Hi, I am Junyi Wu. Today I will talk about our research work, Token Transformation Matters, towards faithful post-hoc explanation for Vision Transformer, accepted by CVPR 2024. First, I will discuss some background on Vision Transformer, VIT, explainability. In this work, we focus on post-hoc explanation, a dominant paradigm for explaining VIT since it can explain the predictions of pre-trained VIT models in a training-free manner. Unlike developing inherently explainable models, post-hoc explanation does not hurt the performance of the original VITs and is straightforward to implement. The problem we aim to address is illustrated on the right. An input image is fed to the pre-trained VIT, which outputs a predicted class, indigo bird. Post-hoc explanations seek to provide the rationale behind the model's prediction. Current methods heavily relies on attention maps to generate explanations for VITs. For example, we can simply extract the attention maps from some multi-head self-attention modules and reshape the first row into the image space. The first row in attention maps represents where the CLS token attends. As shown in the explanation result here, this can localize the bird in the foreground. In this work, we identify a primary bottleneck in attention-based explanation methods. They solely rely on the attention maps in MHSA module, while ignoring token transformation in the entire VIT models. For instance, as indicated in the figure on the right, VITs sequentially perform transformation in layer normalization and MLP modules. Even in the MHSA modules, there are several linear projection layers that process the tokens before and after self-attention. To tackle this bottleneck, we design a novel post-hoc VIT explanation method that inclusively considers the effects of these token transformation, in addition to the attention information. We visualize the distribution of attention weights over the input image here, which exhibits noisy patterns in the background. We also visualize the transformation weights obtained by our proposed measurements and the final explanation result of our expansion method, TokenTM. The transformation weights offer complementary information to the attention weights, demonstrating that token transformation significantly matter in VIT explanation. Building upon this observation, now the question becomes, how can we accurately measure the effects of these transformations on the reasoning process of VITs? We focus on two fundamental attributes of token representation: vector length and direction. We represent tokens as circles with arrows, where circle sizes indicate vector length and arrows point in vector direction. Intuitively, the transformation weights measure the similarity between the original and the transformed tokens. We denote the transformation weights as matrix W, where each term measures the relative length and directional correlation. Specifically, we quantify the token length using their L2 norm and propose the normalized exponential cosine correlation, NECC, to evaluate the directional correlation, serving as positive weighting factors. Then, we integrate the information of both attention weights and transformation weights to produce comprehensive explanations for VITs. Regarding the layered architecture of VITs, we design an aggregation framework to track token contributions across the entire model. Specifically, we initialize the explanation map C using the length of input tokens, denoted as E with superscript 0. We define an aggregation rule recursively for each layer L equals 1, 2, n_L, where n_L is the number of encoder layers in VITs. The update map U here comprises the attention map A, the transformation weights W, the gradient with respect to the predicted class C, and an identity matrix I accounting for the skip connection. By applying the aggregation rule iteratively throughout the model, we obtain C with superscript n_L. The first row of this matrix represents the effects of the initial input tokens on the CLS token in the final layer, so we can extract this row and project it into the image space to visualize the explanation results. To comprehensively evaluate the effectiveness of our TokenTM, we conduct experiments on ImageNet with widely used VIT variants. We assess the impact on accuracy and impact on probability based on the perturbation tests and evaluate the localization ability in a weakly supervised segmentation setting. Results demonstrate the superiority of our explanation method in these three desirable properties. We visualize the explanations of current state-of-the-art methods for comparison. The rationale provided by our TokenTM is clearer and more object-centric. Furthermore, we observe that integrating the token transformation information can lead to a cleaner background, where no C regions are removed from the explanation heatmap. Additionally, we examine our TokenTM's ability to localize foreground objects in complex backgrounds. We provide two representative examples here, one with a bigger object, a dog, in the background, and another with complex shadowing similar to the foreground. We observe that our method can still accurately localize the foreground objects. Moreover, to explore the network's actual attention, we analyze the aggregation process along layer depths using TokenTM. As illustrated below, shallow layers identify semantics in both background and foreground for relational reasoning, which helps recognize key objects in deeper layers for final predictions. To understand the intrinsic principle of TokenTM, we also visualize the distribution of attention maps A, transformation weights W, and their combination in the right figure. Interestingly, W serves as dynamic filters to redistribute A to focus on pivotal token interactions while ignoring less vital ones, especially in deeper layers where long-range dependencies are captured. This results in cleaner explanations, as less vital token interactions are filtered out. Thank you for watching. If you are interested in our paper, please scan to find more details.